Hello and welcome back. In this video, we discuss about the principle of conservation of mass, applied to fluid in motion, using the Reynolds transport theorem. In the previous video, we discussed about the concepts, system and control volume. By definition, a system refers to collection of matter of fixed identity, which may move, flow and interact with the surroundings. For example, a finite amount of fluid flowing through a pipe is a system. On the other hand, a control volume refers to volume in space, through which fluid may flow. The control volume can be fixed in an appropriate space, for convenient analysis of flow. The volume is purely a geometrical entity, and it is independent of mass. When a system moves through a control volume, its extensive properties may change. For example, a change in momentum of a fluid system causes reactive forces on the control volume. In this video, we discuss about Reynolds transport theorem that relates changes in extensive properties of a system to its changes inside and across a control volume. The goal is to derive appropriate mathematical relations that can be used for fluid dynamic analysis of a given flow system. In a control volume analysis, we focus our attention onto the control volume, and observe the motion of system through it. Mathematically, we can show that rate of change of an extensive property of a system is equal to the rate of change of its intensive value integrated over the control volume, plus its net flow over the control surface. This is called Reynolds transport theorem. We will discuss the meaning of each term one by one. dB system by dt is rate of change of an extensive property of a system. For example, it can be rate of change of mass or momentum of the system. In the next term, small letter b is the intensive value of property B under consideration. Meaning of these terms can be discussed next. Raw dV is differential mass of system within the control volume. B raw dV is value of intensive property, for a differential mass of the system, within the control volume. Finally, the second term refers to the rate of change of value of intensive property, for a differential mass of the system within the control volume, integrated over the entire control volume. V.n is essentially the projected velocity of fluid particle to the normal vector of a differential area. This is velocity component normal to the differential area. Raw times V.n dA is mass flow rate through the area dA. Note that, if vector n and velocity v are orthogonal, no mass is crossing this area. Finally, when multiplying mass flow rate with intensive value of system property, and integrate over the entire surface, we see that the final term corresponds to net flow of intensive property into the control volume through the control surfaces. Finally, let us review the Reynolds transport theorem. The rate of change of an extensive property of a system is equal to the rate of change of its intensive value integrated over the control volume, plus its net flow over the control surface. The extensive properties of system can be its mass, momentum and energy. If the extensive property B is mass of the system, then this equation will be conservation of mass. Let us begin with Reynolds transport theorem to derive an equation for conservation of mass of a fluid system. Let the extensive property B, be mass. That is, B system equals m. By definition, the mass of the system is constant. Therefore, dB by dt will be 0. The resulting equation is called continuity equation. The physical meaning is that the rate of change of mass within a control volume, plus the net mass flow across the control surface, will be 0. Or we can say mass can neither be created nor destroyed. Let us simplify the continuity equation for a simple case of steady flow. Since steady flows are independent of time, the continuity equation can be simplified to equation 1. We will use this equation for deriving equation of conservation of mass for a fluid steadily flowing through a pipe in the next video. Thank you for listening.